So first we took this metal tube, which was unattached at the bottom. We attached it, put duct tape over the seam so no air can get out. Then we stuck a 2x4 inside this, which we're going to lean on to drill the holes. Next, we've clamped it down on either end of the workbench, and we put a piece of masking tape in a straight line so we can have some resistance when beginning to drill the hole and the drill doesn't slide off the slippery surface.
Stay left. Maybe it just takes a really long time to fill. Yeah. Tap it a little.
So after my dad and I had finished building the Ruben's tube, we tried hooking it up to the propane to see if that would work. And at first we had some trouble because it wasn't lighting. And then we found out that propane is actually denser than the air. So we had to wait for a few minutes for the tube to fill up with propane and for the air to come out, the tube to fill up with propane, and then when we lit it, it worked. However, we ran into some problems with the wind because it was pretty windy, so the waves that we were supposed to see in optimal conditions weren't as great as they could have been. So the way the Ruben's tube works is there's the little holes poked in. We had 92 holes, a 1/16 of an inch and a 1/2 inch apart, and the propane would be seeping out of the holes. When you light it, there's a little flame in each because there's oxygen at the edge of the tube. So the flames it's all lit, and then we hook up. We had a balloon at one end stretching across fairly taut at one end, and the other end was closed and duct taped so no air could escape. We had a speaker held up to the balloon, and the sound would make the balloon vibrate a little because we didn't want the speaker touching the propane, and that could be dangerous. So if you have a single tone, such as A 440 hertz, what happens in the tube, the sound goes into the tube, and sound is in a wave, sinusoidal wave. It hits the closed end, bounces back, and creates something really cool. So this is what you see. You see the sinusoidal wave pattern of the flames. And what happens is, if you have two of the waves, so let's say we're starting at this end, the sound is coming from this end, this is the closed end. The red is the wave traveling this way, and then the blue is traveling the opposite way. They would really kind of be on top of each other, but I drew them right next to each other. So what happens is, here, this is called constructive interference, and the two waves, the amplitudes, which is how tall the wave is, they add together and make a super tall wave. And that happens in each of these points. Then in these points in between, the waves cancel out and the amplitude is 0. So what this does to the gas is it creates variation in pressure, and the higher pressure forces the propane out, and the flames are taller, whereas when there's destructive interference, there's less pressure and the flames are shorter. So that's why you can see this sinusoidal wave pattern with the flames. So as you can see in this next video clip, this is what it looked like, and the wind still made it not optimal. So next, if you have music with multiple tones and different instruments, the flames, there's a bunch of different waves going in. It's not as clean of a wave like that. So you have the flames kind of dance. And when you have loud, sudden loud parts, you can really see the flames jump up because of the higher pressure. We noticed, partly because the wind made it hard to see clearly, but very staccato sounds, such as a very staccato piano, worked very well in making a visible change to the flames. Now, there are some videos of some of the music my family and I played with.